Hello dear students, in this lecture we will see one more important property of equivalence relation, especially important properties of equivalence classes. See here we have considered an example of equivalence relation congruence modulo 3 and we have obtained the equivalence classes 0, 1, equivalence class containing 2 and equivalence class containing 3. Observe here that equivalence class containing 0 and equivalence class containing 3 are same here. See here, equivalence class containing 0 and equivalence class containing 3 are same. But equivalence class of 0 and equivalence class of 1 are mutually disjoint. And equivalence class of 1 and equivalence class of 2 are also mutually disjoint. Equivalence class of 0 and equivalence class of 2 are also disjoint. So from this we can say that any two distinct equivalence classes are either mutually disjoint, that is no elements in common, or they are same. That is, it does not happen that the two distinct equivalence classes has a non-empty intersection. If there is a non-empty intersection, then the two equivalence classes must be equal. This is the property, and this property we have to prove this property. So equivalence class of 3 and equivalence class of 0 are same. Similarly, equivalence class of 4 and equivalence class of 1 are same. Already we have proved this property, that is x belongs to equivalence class of y if and only if equivalence class of x equal to equivalence class of y. Okay. Now we are going to prove that this theorem, that is the property, let R be an equivalence relation on a set A, then any two distinct equivalence classes are either disjoint or equal. We have seen that the equivalence classes 1 and 2 are disjoint, but the equivalence classes 1 and 4 are same. Equivalence classes 1 and 4 are same for the previous example, congruence modulo 3. We have to prove this. So we have to take two equivalence classes, and if they are not disjoint, then we have to prove that they are equal. So let x comma y belongs to x be any two distinct elements, then we have to prove that then equivalence class containing x and equivalence class containing y are either disjoint or equal. So suppose equivalence class containing x and equivalence class containing y are not disjoint. Means what? That is, equivalence class containing x intersection equivalence class containing y is not empty. That is, some elements belongs to equivalence class of x and some element belongs to equivalence class of y. This implies that there exists W belongs to equivalence class of x intersection equivalence class of y for some W belongs to x, because this is going on the whole set, on the set x. So this implies that W belongs to equivalence class of x and W belongs to equivalence class of y. Now we have to prove that we have assumed that these two are not disjoint. We have to prove that these two are must equal. This implies that W is R related to X and W is R related to Y. This implies that X is R related to W and W is R related to Y, as R is symmetric. This implies that X is R related to W and W is R related to Y, and by transitivity we have X is R related to Y by transitivity. Transitivity property of R. We have to prove that X and Y. We have to prove that equivalence class of X is equal to equivalence class of Y. How we can prove? We have to prove that each element in equivalence class of X is in equivalence class of Y, and each element in equivalence class of Y is in equivalence class of X. But we have already proved that X is R related to Y. Here we have X is R related to Y, and we have already proved that. What we have already proved? That is, X belongs to equivalence class of Y if and only if equivalence class of X equal to equivalence class of Y. So by using this first theorem, we can see that this implies that X is R related to Y means X belongs to equivalence class of Y. So by using the previous theorem, X belongs to equivalence class of Y, then we must have this implies that equivalence class of X is equal to equivalence class of Y, because we have already proved that if X belongs to equivalence class of Y, then equivalence class of X and equivalence class of Y are same, one and the same. See here, X belongs to equivalence class of Y if and only if equivalence class of X equal to equivalence class of Y. So what we proved here? If equivalence class of X and equivalence class of Y are not disjoint, then they must same. From this we can see that any two, therefore any two equivalence classes are either disjoint or same. Hence the proof. Thank you, students.